Hello everyone. So, welcome to lecture 42. So, we were looking at dissipation, dissipative properties as properties that relate a force and a flux, right. And then so last class we ended the last class by saying uh, by trying to we started building a mathematical framework to actually show what is the dissipative power, which is T s dot, and we want to actually by the end of this class show that this T s dot is nothing but it is equal to V I or f x dot and things like that, right. So, so we ended so in the last class we were actually looking at the conservation loss. So, we started with du, right, and then we said we end up if we put in time into the problem where all these quantities are not at equilibrium, the system and surroundings are not at equilibrium. So, with time there is an evolution of the system and of course, the surroundings. So, then the entropy is changing with time, of course, right. So, entropy is being exchanged between system and surrounding, but there is new entropy that is being generated. Okay. So, there is an S dot term. We are interested in looking at what that S dot is, because that tells me what dissipation is, but that is also related to the dou u by dou t and dou E by dou t. Okay. So, and then we said alright. So, for something like I have volume conservation, so I have something like not volume conservation, but I have something like charge conservation, right. So, for example, this one is something like charge, right. So, I have charge conservation, I have energy conservation, right. So, if some certain things are conserved, like charge is conserved, right. So, or energy is conserved dou u by dou t, I can write the conserved quantity as nothing but minus del j u plus that is it, right. So, this is a conserved quantity. These are my autos that go in and they should definitely come out. They can come out slow, but they should definitely come out, right. So, it is a conserved quantity, right. Similarly, so if epsilon is representing my charge, right. So, charge flow, dou epsilon I by dou t should also be a conserved quantity of epsilon I, right. So, the flux of so again I have to I will tell you in the next class what this is exactly called, but for now let us just call it epsilon for lack of so for my bad memory, right. So, let us excuse my bad memory and call this epsilon for now. Okay. Okay, alright. So, this is also a conserved quantity. This is a conserved quantity if I am talking about charge, let us say, right. So, flow of charge, flow of atoms, etc., right. But if I am talking about flow of volume in mechanical scenario, this is not conserved, right. So, if a volume does not need to be conserved, right. So, yeah, so there is that distinction, but okay. So, atoms are conserved. Let us look at atoms, right. So, flow of so any sort of stretching as flow of atoms, not really flow of volumes. Okay. Okay. So, then however, if I look at dou s by dou t, however, this is a non so I am going to write it in a different color because this is not conserved. Okay. Minus del dot j s sorry yeah, so minus del dot j s plus s dot. Now I have my term that I am looking at, right. So, I have this S dot term, and S dot term represents my entropy generation. Okay. Now, this is the term that I want, right. So, by doing this conservation loss and expressing the changes in entropies and internal energies as fluxes, I got this entropy generation term. Okay. Alright. So, now let us go back to that equation. So, I am going to say okay dou s by dou t equal to 1 by T dou u by dou T minus 1 by T psi j dou epsilon j by dou T. Okay. So, this is summation over j. So, this can be electric field or so in some sense this is a potential. So, this can be voltage in applied in the j direction, and this can be flow of charge in the same direction, right. So, dq j by dt or current in that direction, right. So, I am associating some sort of directionality to the voltage that I am applying and the charge that I am applying, and so that can be or E1 dP1 or dq1 by dt, right, or E2 dq2 by dt, those sort of things. I can sum out all these electric field and charge, right. So, flow of charge. Okay. So, anyway, so that is why I have a summation there. All right. Now, if this is the equation, I am just going to write this as minus del dot Js plus S dot, okay, equal to 1 by T, and I am going to just write this as minus del dot Ju, okay, minus 1 by T, and I am just going to write this as, or I can take 1 by T inside sigma j, and this will be minus del dot j epsilon j, this is sigma over j. Okay. All right. So, now I have so I have something which looks like this is a derivative of something, and this is just a normal scalar quantity, right. This is a derivative, or this is a gradient. I am sorry, this is not gradient, this is divergence of a vector, right. So, I mean in very simple terms it looks like A differential of B, right. So, irrespective of whether this is vector or scalar, right. So, this is a very simple way in which it looks like, and this I can write it as dAB minus A B dA, right. So, that sort of a thing, right. So, this is just the chain rule, right. So, I can express AB as BdA plus AdB, right. So, if A, B, C everything is scalar, but here we have some vectors, and in vectors this just becomes A del dot B equal to minus B gradient of A. Now, here B is a vector and A is a scalar. So, I am always going to look at dot products. If this is a vector, I take the divergence and I just multiply it with another scalar. So, eventually I should get a scalar, but if A is itself is if B is a vector and A is a scalar, then I take the gradient of it, this is called the gradient, right, and then I take a dot product, so that eventually I get a scalar, right. So, this is how I do this, plus del dot A B. Okay. All right. So, this is also a scalar, right. So, now I have all these terms, right. So, are in this form. Okay. So, if I just look at del dot Ju 1 by T of that, I am going to write it as minus Ju that I am going to, that is going to come out gradient of 1 by T, right. Okay. Then I have summation psi j by T and then del dot j this thing, right. Now, that I am just going to write it as okay. So, plus del Ju by T, right. So, this is just using the chain rule. So, this also I am going to just write it as summation again over j. This time I have j epsilon j comes out dot, this is a vector, the flux is a vector, gradient of this potential divided by temperature, okay, plus again I have the this is minus of this plus epsilon j by T times sigma j, okay. All right. So, now I am going to write this all here, so in this equation, this is the equation of interest, equation 1 I am going to call it. So, now substitute equation 2 and 3 in 1. So, what I get then is so minus del dot J s plus S dot is equal to minus del dot, I am going to combine this term and this term, sorry let me just write it in red, I am going to combine this term and this term, right, because everything is a del dot, it is not a gradient, sorry, it is a del dot, right. So, it is a divergence, right. So, this is the okay. So, j is a vector, right. So, I have a divergence there. So, that would be j u by T, right, plus j epsilon j psi j by T, all right, good. Then plus I have S dot term. Now, S dot is okay. So, let me write it as this 1 by T, okay. This is minus of yeah. So, there should be minus here, okay. So, yeah, so there is a minus here and minus here, that is okay. So, this will be plus, sorry, this is minus and this is plus. So, when I go for minus, this will be plus and this will be minus. So, this is plus minus sigma j epsilon j dotted with the gradient of psi j by T, okay. So, now if I compare these equation, this is equation 4, if I compare these, then what I get is the divergence term, the Js term is actually this term, right. So, this is just divergence of something else. So, that is my Js, okay. What I am actually interested in is in S dot, right. So, just by comparing one on one these two things, I have S dot is equal to, let me go back from equation 4, I am just going to write this entire expression as S dot, right. So, J u 1 by T, okay, minus sigma j epsilon j and del dot so gradient of psi j by T, right, psi j by T, okay, great. All right. So, now we can have some more simplification here. So, so I want eventually I want to see this in terms of heat and heat flux. I do not understand what the flux of internal energy is, but I understand what heat flux is, right. So, I want to convert J u as J q. So, J u again I just go back to first law of thermodynamics and I put it in terms of fluxes. J u is J q plus the work that is done, right. So, d u equal to d del q plus del w, right, and the work that is done is psi j epsilon j, okay. So, this conversion I am going to do. So, this is equation 5. In equation 5 I am going to write S dot equal to J u, or instead of J u I am just going to write J q plus okay. So, J q gradient of 1 by T, right, minus, okay. So plus sigma sigma psi j epsilon j minus, right, I am going to term these things together, j epsilon j dot gradient of psi j by t, right. So, this is yeah. So, there is going to be a del 1 by t here, sorry, gradient of 1 by t. Okay. So, this dotted with gradient of 1 by t, this dotted with gradient of psi j by t. Okay. So, that will just be equal to j q times by t square, right. So, minus of this and I am just going to write it as del t, okay, or gradient of t plus now again. So, this looks like, so I am just going to take out j e j outside, right, and I am going to put in a minus, right. Yeah. So, this is okay. So, then if I put a minus outside, then what I have is dotted with gradient of psi j by t minus gradient of minus psi j dotted with gradient of 1 by t, sorry, psi j gradient of 1 by t, right. So, there is no dot product here, it is all, everything is a scalar, right, except when I do the gradient I get a vector. Okay. Now, what is this? This again I have an A B sort of a rule, right. So, this is again, you know, this is like del A B, right. So, or gradient of A B is equal to B gradient of A plus A gradient of B, right. So, both of them are scalars now, right. And so, I will just write that, you know, so that is equal to, so I will use this expression and write this as minus j q by t square gradient of t minus j epsilon j, right, dotted with, now I am just going to write this as you know, yeah. So, I have a gradient of psi j 1 by t, right. So, this is what will come out, that is this term, right. So, it is this minus this equal to this, right. So, that is this term, all right. Now, I have something, so I have s dot, this is all equal to s dot, right. So, this is my equation 6. I send the t that side, so now I have t s dot, I am almost there, equal to minus j q by j q, I will say you know, gradient of t by t, right, and I have maybe I just missed some terms here, yeah. So, I think this should be a plus, yeah. So, again pluses and minuses, there is some confusion, but that is probably okay. No, it's fine, it's all minus, that is okay. So, j epsilon j, this time what I have is just del psi j, okay. So, let us stare at this equation, right. So, this is the equation of interest for me, this is 7, okay. All right. Now, what is this? This is again what I said is, this is the definition of power dissipated, okay. Now, power dissipated is nothing but, if I have a flux, you know, and I look at the gradient of a potential. Now, gradient of potential is what? Psi j is some sort of a potential, right. So, psi j times j you know, so gradient of a potential, that is nothing but my force, correct. Now, what is this gradient of potential? If psi j is my electric field, sorry, is my voltage, gradient of voltage is the electric field, that is the force, right. And the flux is you know, so if E is the force, right, and the flux is actually j q, or J or flux of charge carriers, right. So I have flux of charge carriers times E in some sense, right. Now that is J E. J E is nothing but power dissipated So this is the power dissipated per unit volume, electrical power, let us put it that way, electrical power dissipated per unit volume, right. So, if I if I do not do it per unit volume, then I have V I, right. So, sorry, then I have V I, this is non volume normalized. Okay. So, essentially I said T S dot is the same as J dot E, right. So, I in electrical domain, in power in electrical domain, and similarly T S dot or T capital S dot, right. So, if I am not volume normalizing it, is equal to V I, right. So, this is also power dissipated, right. Then if I have flow of atoms, this is flow of charges, right. If I have flow of atoms, then so J I is the dissipation, so J I is the flux, and the force will be given as if I just go back here, that will be the gradient in concentration or gradient in what is called chemical potential of these atoms, right. So, this is the chemical force, this is the chemical flux, and so the chemical flux times chemical force is nothing but T S dot again, right. So, T S dot is my power dissipated, and that is equal to minus of the flux times force, right. So, flux times force gives me dissipation or T S dot, entropy generation or energy dissipated. Okay. So, that is why we keep saying V I product is nothing but joule heating, right. We just do not ask the question why is it actually heating, I am just multiplying voltage with current, right. How is it equivalent to heating a material? It is fundamentally, it comes from this sort of a derivation where you are saying that T S dot thermodynamically just dissipating heat is equivalent to T S dot, and if I look at the work done, which is electrical work done, and see how much is the flux of the charges that are flowing, then that V I is nothing but T S dot, right. So, I have proved it to you. So, what you have been assuming so far. Okay. Similarly, flow of atoms in diffusion problem, right. So, if I have a chemical gradient, if I have a chemical potential, and if I have a gradient, so gradient of chemical potential, that is my driving force, chemical driving force, which drives the atoms to move from a higher chemical potential to a lower chemical potential, or higher concentration to a lower concentration, right. So, that is diffusion, that process is diffusion, but so the flux times the force gives me the dissipation. Okay. So, so that is with respect to flow of atoms, right. Now, there is one more important thing here. If you look at the thermal energy dissipated, right. So, okay, so T S dot is the total power dissipated, it is in all domains, but I can just dissipate it just by so if I have some heat flow, this is heat flow times del T by T or gradient of T by T, right. So, this looks like the force, right. So, this is flux and this is the force that this is sort of a thermal force in some sense, right. So, if I have heat flow times the force, flux times the force, and that force, thermal force, is just gradient of T by T, or in other words, that is J Q times gradient of ln T. Okay. So, now this is so the thermal force equivalent for dissipation is actually gradient of temperature. If I have if I have some bar with a temperature T1 here and T2 here, right. So, I have a gradient of temperature, this exists, and when there is a gradient of temperature, heat flows, right, and the flow of heat times the gradient of temperature by temperature, or in other words gradient of temperature log of gradient of temperature, right. So, sorry, gradient of log temperature, right. Now, that is my thermal driving force for heat flow. Okay. Okay, all right. So, I have a flux, I have a force, and this force can be chemical, this force can be electrical, this force can be, I mean, I am not specifically saying mechanical because mechanical forces, mechanical fluxes are not conservative in nature, but just for completeness I am going to say this force can be mechanical, that is, so just the just the force that I apply on a spring mass, right. So, I have a mechanical potential which is given as F dx, right. So, F d delta, rather this is the total potential V m, right, and the gradient of this, right. So, gradient of V m gives me the mechanical force, that is nothing but F, right, and what is the flux it generates? It generates a flux of spring that just keeps extending, right. Now, there is no conservation there, you have to also look at there is no conservation of volume there, for example. So, it may not exactly work out, but okay. So, just for completeness I am just going to say that there is a gradient of mechanical force. This force can be thermal force, which is nothing but delta T by T or gradient of T, and the flux is going to be atom diffusion or ion diffusion. The flux is going to be charge migration or charge flow, Ohm's law comes from there. The flux can be just strain flow or material flow, the flux can be just heat flow, right. So, all these, right. So, just this flux times force gives me dissipation or T s dot. It just heats up the it just loses the energy that you are supplying, right, in the form of heat, right. So, it is just gone. Okay. So, even when heat is flowing, right. So, I mean you can have a temperature, you can generate heat, but then you can sustain it, right. So, but this is it, if heat is flowing through some thermal force, through some gradient of temperature, then that heat is just gone, right. So, that energy is just gone, right. So, it just dissipates. Okay. So, with that let us stop this lecture here, right. So, it is a short lecture, but I just wanted to show you that how this power dissipation in the form of T s dot is exactly the same as power dissipation in the form of V I, electrical power dissipation, or in a diffusion problem, how this is exactly the same as the diffusion flux times force in a diffusion problem, flux times the chemical gradient, chemical potential gradient, or in case of a spring mass system, how it is exactly equivalent to a force times the strain gradient, right. So, all these are how I calculate the dissipation in all these systems. Okay. Mechanical is an exception because we do not exactly say F times x dot is the power dissipated, there is also some sort of other mechanisms that do not conserve volume, right. So, that do not necessarily conserve volume, but if I am conserving volume then I can just say F x dot. Right. So, in a creep problem, if I am conserving volume, if I assume that I am conserving volume, then I am just going to say F times x dot is the energy that is dissipated, mechanical energy that is dissipated in the form of heat or whatever, right, in the form of heat exactly. Okay. Okay. So, with that let us conclude here and let us take it up from this point onwards, where I have defined a flux and I have defined a force, and I said I multiply these two, I get dissipation, right. Now, in the next class we are actually going to see how is what the property did not come yet, right. So, how is flux related to force, that gives me the dissipative property, and in the next class we will actually look at these dissipative properties. Okay. So, with that let me say goodbye for this class. Thank you very much.